All right, today we're going to be talking about the tangent function. And to do that, we're going to relate it just like we have with sine and cosine. We'll relate it to the unit circle. So I have a picture of unit circle here. And in this unit circle, we have a random angle called theta. A point happens to be in the first quadrant in this scenario that has the coordinates x comma y. All right, now you're totally used to this by now. We've talked about sine and cosine. We need to talk about what tangent is. So as a working definition that we're going to use, tangent is equal to y over x. I want you to just take a look at that. Think about it for a second. What does y over x kind of look like that we've done before? Right, your answer should be that y over x looks a lot like slope. And that's pretty much exactly what's going on here. Tangent is the slope of the line connecting the origin to the point that you are on the unit circle. So as we kind of roll through this a little bit, we want to keep in mind that tangent is representing slope. Okay. Now the next thing we need to develop is just how would we actually calculate that from other things that we have. So again, don't forget that this is y, this is x, but we also have other names for these now if we're talking about the unit circle, and that would be sine over cosine. And we want to keep that relation in mind too, because maybe we've been given the sine value and the cosine value, and if we've been given those, then we essentially know our y and x, and then therefore we can find a particular tangent value. Okay, so let's think about this then as far as what's actually happening to the slope, to the tangent, as we go around the unit circle, starting at 0. Okay, so at 0, we are going to have a slope of 0, a horizontal line. As the point moves this way, what's going to happen to the slope? You're correct if you said it's going to increase. All right, so it's going to continue to increase over and over and over again, increasing, increasing, increasing. Okay, what kind of slope would this be if I made a line right here? How big or what size slope would that be up there, if you could guess? That might be a slope of 10, 20, 30. The closer I get my point to the top here, to the 90-degree mark, it's becoming increasingly bigger, like even crazier than exponentially bigger. All right, so we start at 0 for our slope. We get big, 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 crazy big, and then from there, it'll be undefined. Okay, we got a vertical line here. And then it'll go back to really big, but big in a negative sense. As soon as our point is over here, now we have a negative slope. The slope is going down and to the right instead of up and to the right. So now we have to remember, okay, we've switched over to a negative slope, and it's getting less negative to 0. And then it's going to get positive again. It's going up and to the right. And it's going to, again, start at 0 and get more positive, more positive, more positive, undefined at this point. And then it's going to be a negative slope again, all the way until this point. So the next question would be, what is the slope, what is the tangent at a 45-degree angle? What's tangent of 45 degrees? All right, well, think about your 45-degree angle. How does the y compare to the x? Oh, they're the same. They're both square root of 2 over 2. So if I have my y value, square root of 2 over 2, divided by my x value, which is also square root of 2 over 2, that looks really, really complicated, but I have the same thing on both sides of the fraction, so basically that's going to be 1. So at my 45-degree angle, I have 1. I started at 0 here. 0 as my angle, 0 is my slope. Here's 45 degrees as my angle, and 1 is my slope. And by 90 degrees, I have an undefined slope. It's vertical. All right, so now what we're going to do is we're going to take a look at the graph, and then we'll come back to calculating tangents of various points in just a second. All right, so here's my point. Or sorry, not my point. This is where we're going to graph the tangent function. And the tangent function, as we said, at 0 is 0. And then at 45 degrees, oh crap, I don't have degrees on here. Where's 45 degrees? Yep, that's pi over 4. Okay, at pi over 4, it's going to have a value of 1. Okay. Now, pi over 2, what angle is that? That's 90 degrees. Okay, remember at 90 degrees, what was happening? I had a vertical line, undefined slope, but right up to that point, it was becoming really, really big, infinitely big. So by the time I get to pi over 2, I'm going to be so big, I'm going to be off the page. And so what we're going to do then is we're going to create what's called an asymptote. And I know we've talked about this before, but we're going to create an asymptote here. And that's going to show us, hey, there's not a defined point right here, but it's defined leading up to that. So this is what tangent function looks like, starting at 0 and going through 45 and then up close to pi over 2. It's going to look like that. All right, and then if you remember, going to our unit circle, after pi over 2, we have a negative slope, a really big number that's negative slope, going to 0 and then getting back higher again. So if I look at my next piece, I have a really negative slope. At the next 45 degree angle mark, it's going to be -1, which is right there. And at the next mark here at pi, it's going to be 0. And so I have something that looks kind of like this. Now that'll continue, and we'll talk about how it continues next. Now I'm going to go backwards. All right, so if I go backwards in my unit circle, if I go down from 0 degrees instead of up, I go back to a negative small angle, negative bigger angles, to here undefined, and then I'm back to positives again. So at negative pi over 4, so 45 degrees clockwise, I'm at -1. And then by negative pi over 2, once again, I'm at an asymptote where I have a vertical line, and so I have no slope. So this one is going to curve out this way over time. So this is essentially one period of the tangent function. Tangent's period goes from negative pi over 2 to pi over 2. So that would be pi radians, or 180 degrees is the period for tangent. And so it would continue to happen like that over on this side. Okay, do the same sort of thing there. And on this side, it would look like this. So it's still a periodic function, but the period's a little bit different than sine and cosine. And of course, it's not wavy. It actually has breaking points every so often. And so that's the difference between tangent and one of your sine or cosine sorts of things. All right, so then the next thing we should probably do is take a look at the unit circle and learn how to deal with this whole tangent function as far as finding tangent of a certain angle measure, something like that. So put that away. Here's this, and then I'll use a little note on top of that. So here's our unit circle. We'll start there. And so I'm going to do, let's do a different example. So I want to find the tangent of a, let's say a 120 degree angle. All right, tangent of 120. So I can find 120. 120 is right here, and I know the x and the y coordinate. So what I want to do then is I want to take this and remember to do the y coordinate over the x coordinate. That's going to be the square root of 3 over 2 is the y coordinate. And then -1/2 is the x coordinate. when I simplify that, the first thing I could notice is both of these are divided by 2 or over 2. So that actually kind of undoes itself. And so really it's the square root of 3 over negative 1. And the square root of negative 3 over 1 is just negative the square root of 3. So that would be what we call the exact answer for tangent of 120. In fact, if you take a look at all these unit circle values, if they're not 1s and 0s, then they're over 2 every time. So a little trick here is that I don't really have to, and I'm going to give a different example here. If I do tangent of, for instance, 210 degrees, I don't really have to do anything with the whole fraction on both sides. I can really just focus on the numerators, and that'll actually help a lot. So, for instance, the y-coordinate of 210 degrees is negative 1/2, so I'm just going to put the negative 1 part of that, and then the x-coordinate is negative radical 3, and just put the numerator of that one, and then I could simplify this. That's going to be 1 over the square root of 3. And I'm going to tell you right now, I'm actually okay with you leaving it like this. But oftentimes they like to rationalize that denominator. And so this is actually the answer you should have, square root of 3 over 3. And I'll tell you, when we're doing exact values, just like we did with sine and cosine, you're only really going to deal with 3 different numbers. Or not 3, 5 different numbers. You're going to have negative radical 3, or sorry, not right. You're going to have something with radical 3. Sometimes it's negative, sometimes it's positive. And that's when the radical 3 over 2 is the y-coordinate. Or you're going to have radical 3 over 3 when the 1/2 is the x-coordinate, or the y-coordinate. And then you're going to have 1, the tangent of any of your 45-degree angles, like 315 for instance, is going to be the same number over itself, and then maybe one of them is negative. So for instance, this one's going to be negative radical 2 over radical 2, which is going to be negative 1. So you have those 3 numbers, and then when the y-coordinate is 0, you're going to have a slope of 0. So we have a slope of 0 at 0 degrees and at 180 degrees, or 0 and pi radians. And then we'll have an undefined slope for these two. Any rotation of pi over 2 or 90 degrees, and any rotation of 3 pi over 2 or 270 degrees will give you a slope of, or what we call undefined. So it's these 3 numbers, then also 0 can be a slope, and undefined are the only choices you have for tangent exact values. Now again, I'm talking about exact values here. So let's throw in a little curveball to make sure we're still remembering things from the past. If I do tangent of 84 degrees, how are we going to do that one? All right, we need to know the y-coordinate and the x-coordinate. How do I find the y-coordinate of 84 degrees? Yep, I'm going to do sine of 84. Okay, how do I find the x-coordinate? I'm going to do cosine of 84. All right, so I'm going to get my calculator out now, and I'm going to do sine 84 over cosine of 84. And then some of you are already realizing, do I have to do this? And we'll talk about why you do or do not in just a second. So sine 84 divided by cosine 84. I'm going to double check that my mode is in degrees. Yep. Hit enter. And I'm going to get 9.51. All right. And if you think about that, 84 degrees is up here. That's going to be a pretty steep slope, so 9.51 makes sense. Okay, so the trick here that we have to remember is if we actually are given the degree measure, you could just put in tangent of 84, and it should give you the same exact answer. All right, so I didn't want you to freak out when you knew that that was sitting there to do tangent. So where this information would be useful then is if I tell you I have a point and I know it's x and y coordinates, but I can't tell you what angle it is, you can still find the tangent because you have the y and the x coordinates. All right, so that's a situation where that would be useful. All right, so I'm going to do a quick recap because I think that pretty much catches everything you need to know. And then we will move on from there. Oh, there is one other thing I need to show you. Okay, so recap real fast. Tangent is slope, and it's equal to sine over cosine. So tangent's the slope of the line connecting the origin to your outermost point. Tangent's graph looks like this. Get this out from underneath. All right, where it has kind of this S sort of shape, or this, turned S sort of shape going on. And it goes from negative pi over 2 to pi over 2 if it's just the function y equals tangent of x. Okay, now as soon as we make any changes to that, then that'll change, maybe the period or where it goes midline and stuff like that. So as an example, let's graph on this same coordinate plane y equals 2 tan of x plus 2, something like that. All right, again, we just need to think about this in the same way we do with the sine and cosine functions or with transformations. So the 2 is kind of like the amplitude, but the amplitude is infinite on a tangent function, so we want to be a little bit more specific and just say, well, it stretches by a factor of 2. So that means each point will be twice as high. So I'm going to do in between here. So this point will be up there, and this point will now be way up there, which means essentially whatever I had at 2 is now going to be at 4. That'll help me a little bit. And then same thing over here. Whatever was at negative 1 is now at negative 2. Whatever was at negative 2 is now at negative 4. And so on. Okay. So now I have that function. And then this plus 2 right here, that plus 2 right there, will tell me to increase all of my points by 2. So this one goes up 2 units, this one goes up 2 units, this one goes up 2 units, 2 units, and so on. And then I still have a graph that just got stretched and shifted a little bit. All right, so that's the only other thing you'll probably see. We'll work through that in class a lot too. Hope that works for you, and I'll catch you next time.